Welcome. In previous videos, we've looked at how to calculate velocity if you're given displacement data. In this video, we're going to look at it the other way around. How can you calculate displacement if you're given velocity data? So to start off, we're going to set up an example that we can use later on to calculate displacement from velocity data. So first of all, we'll generate some velocity information and then try to go backwards. So in this example, we've got a cyclist, and they're doing maybe some kind of time trial, and they're crossing known marks at 9 meters apart, and we're timing them. So we're timing when they cross each 9-meter mark. In this case, they're crossing each 9-meter mark at 1 second intervals. So after 1 second they have a displacement of 9 meters. After 2 seconds they have a displacement of 18 meters. After 3 seconds they have a displacement of 27 meters. And after 4 seconds they have a displacement of 36 meters. So a plot of that data looks like this. And you can see that if we look at the slope in this first interval, we have a 9-meter displacement over a 1 second span. But if we look at it, the cyclist crosses 9 meters every 1 second span in this particular case. So the slope all along that line is the same. So if we look at that overall, each interval has a rise of 9 meters and a run of 1 second. So the slope at every point in time along that graph is 9 meters per second. So in other words, the cyclist is riding with a constant velocity of 9 meters per second. So let's look at this a similar type of example, but we'll change it up a little bit, and we'll say that the person still crosses the first 9-meter mark at 1 second, but then crosses the 18-meter mark at 3 seconds, the 27-meter mark at 3.5 seconds, and the 36-meter mark at 4 seconds. So if we plot that displacement versus time, we get a graph that looks like this. So one question we can ask is, what is the overall average velocity? How is that different from the previous one? And so if we want to look at the overall average velocity, we want to look at the total displacement over the total time. And in this case, the total change in displacement is 36 meters, and the change in time is 4 seconds. And so we get an average velocity of 9 meters per second, which is actually the same as the previous graph where the person was going at a constant velocity, because they've still crossed the same 36 meters in the same 4 seconds. But obviously in this example, they're not going at a constant velocity. Their velocity is changing. So this is another example that we've seen previously when we talked about instantaneous versus average, that the average velocity is quite often not the same as the instantaneous velocity. So in both of the previous two examples, the average velocity was the same, 9 meters per second, but the velocities at any point in time are not the same. So let's take another look at this. So we know that the velocities are not the same across here, but let's take a look at what the different velocities are in the different sections. So in this first 1 second section, the displacement is 9 meters over a time of 1 second. So that would get us an average velocity of 9 meters per second across that first second. From the 1 second time point to the 3 second time point, the cyclist is traveling again 9 meters, so 18 minus 9, except the time period is a full 2 seconds. So that would be 9 meters divided by 2 seconds, which would give us an average velocity of 4.5 meters per second across that time period. Now if we look at the last two time periods, going from the 3 to 3.5 seconds and 3.5 seconds to 4 seconds, in each one of those intervals the cyclist is traveling 9 meters over a half a second. So from 3 to 3.5 seconds, the rider goes from 18 to 27, and from 3.5 seconds to 4 seconds, the rider's going 27 to 36. So in each one of those, they're going 9 meters over a span of half a second, which would give us a velocity of 18 meters per second. And both of those sections are the same slope. So we have the cyclist going 3 different velocities across those 4 seconds. 9 meters per second across that first second, 4.5 meters per second across that middle section, and 18 meters per second across that last section. So we're going to use this information from this example a little bit later to look at how to get displacement from velocity. So if you can get velocity from displacement, which we've seen previously, we can actually also get displacement from velocity. So how do we do that? Well, let's start with a really simple example. So if I'm walking down a hallway with an average velocity of 2 meters per second, and I walk down that hallway for 4 seconds, what's going to be the magnitude of my displacement? Now this isn't a really tough example. If I'm going 2 meters every second, so here's 2 meters for 1 second, and I do that for over 4 seconds, so another 2 meters, another 2 meters, another 2 meters. So I travel 2 meters every second for 4 seconds. It's pretty easy to tell that my displacement is going to be 8 meters. So if you think about what you did to get 8 meters, if you calculated that in your head, what you did was you took the velocity and you multiplied it by the time. So 2 meters per second times 4 seconds gave us 8 meters. And we could actually get that formula from our original formula of how to calculate velocity. So velocity was the change in displacement over the change in time. And if we just rearrange that formula, so we multiply both sides by time, we can get a formula for displacement if we know velocity. So the displacement is actually equal to the average velocity times the change in time. So the concept of going from displacement to velocity, or finding the slope, that was the derivative. So going the other way, going from velocity to displacement, we need to integrate, which is the opposite of derivative. So a simple graphical example of this is the graph of that question. So traveling 2 meters per second down the hallway for 4 seconds. That's what it would look like. So I'm going at a constant velocity across the 4 seconds. And we saw from that previous formula that if we want to know the displacement, we need to know the velocity times the change in time. So if we look at this graph, there's a quantity in that graph that matches that formula. It's actually the area under that curve. So the area under that curve would be that rectangle, which would be the base times the height. So the base in this case would be time, so the 4 seconds, and the height would be the velocity, that's 2 meters per second. And so our displacement would just be the area under that curve, or 2 meters per second times the time of 4 seconds. In other words then, the integral, or to integrate, is to find the area under the curve. So going back to our previous example, we looked at the cyclist and we calculated the cyclist velocity at different points in time along their run. What we'd like to do is now make a plot of the cyclist's velocity over time. So we have the displacement and we calculated the velocities at different times, and we'd like to now plot the velocity over time. So over that first second, from 0 to 1 second, the cyclist is going at 9 meters per second, and the slope is not changing across that first second. So the cyclist is going at a constant 9 meters per second across that first second. So if we were going to plot the velocity from the first second, from 0 to the first second, that would be a straight line, or constant velocity of 9 meters per second. So across that second section, from the 1 second time point to the 3 second time point, the cyclist is moving at 4.5 meters per second. So if we were going to plot that velocity, so from the 1 second mark to the 3 second mark, the cyclist is moving at a constant 4.5 meters per second. So we draw a straight line at 4.5 meters per second. And in that last second, the cyclist is moving at a constant 18 meters per second. So if we're going to plot the velocity of that, it would look like this. So now we've got a plot of the cyclist's velocity across the 4 seconds. So they're going from the 9 meters per second to the 4.5 meters per second, back up to the 18 meters per second. And so from that velocity graph, we'd like to be able to calculate the displacement, but let's figure out what our answer should be so we can go back and compare it to make sure that we're getting the right answer. So from this graph, we can figure out what the final displacement should be. If we look at the final time point, the displacement is 36 meters. So if we take the information from the velocity graph, we should be able to calculate back total displacement of 36 meters. So here's our velocity graph. If we find the area under that curve, from the previous slide, we know that that area under that curve should be 36 meters. So we've got a curve that has a bunch of different sections like that, and the best way to tackle finding the area under a curve like that is to break it up into chunks that are easy to calculate. So in this case, we could break up this entire graph into 3 rectangles, and it's pretty easy to calculate the area under a rectangle. So we'll take a look at this. And so if we add up the 3 areas under the rectangles, we should be able to get the total area. So that first area, going from 0 to the first second, the area of that rectangle would be 9 meters per second times 1 second. In other words, 9 meters. So the displacement from 0 to 1 second would be 9 meters. In that second section, going from the 1 second mark to the 3 second mark, the area of that rectangle would be, it's 4.5 meters per second high and 2 seconds wide, which would give us a displacement of 9 meters. So over that span from the 1 second mark to the 3 second mark, the cyclist is traveling another 9 meters. And in that last rectangle, the height is 18 meters per second and the width is 1 second. So the area of that last rectangle is 18 meters. So from the 3 second mark to the 4 second mark, the cyclist has traveled another 18 meters. So if we want to look at the total area, or in other words, the total displacement of the cyclist, we add up those 3 sections. So 9 plus 9 plus 18 gives us a total displacement of 36 meters, which we know from the previous slide is the correct answer. So to summarize, as we saw before, if we have a displacement curve, the slope of that displacement curve, or the derivative, is equal to the velocity. In this video, we've seen that if we have a velocity curve and we take the area under that velocity curve, we can get back the displacement. So the slope, or the derivative of a displacement curve, is the velocity. The area, or the integral of a velocity curve, gets us the displacement.